Okay, we're going to look at the thing I'm sending out, which is to do with the appropriate methods of integration. So if you look through it, it says if it's this type, this is what you do. I've got a couple of things just to fill in at the end though, so we'll get to that later on. So it says, number one, standard forms, so things that are just basic-ish year 13 integrations. So integral powers of x, 1 over x you can now do, e to the x, sine x on its own, even sec squared, because you're thinking, if you're not quite sure, you can always look in your formula book at the differentiation integration pages. If you can differentiate something to get, say, sec squared, like tan in this case, then you can integrate sec squared to get back to tan. It might be that you've got a little bit of undoing of chain rule to do. So it says here, simple variations of the standard forms by inspection, by substitution. So by inspection is basically looking at the fact it's cos 3x plus 2, differential sign is cos, so the integral to cos is sine, so it'll be sine 3x plus 2, but because of the 3, you've got to divide by 3. E to the 5x over 5, and so on, like that. You know, in this case here, I would have differentiated x plus 5 to the power 5. So you can think about, in this case, it would be 2x plus 5 to the 5, all divided by 5. And so you can either do it by substitution, by inspection. Inspection is basically differentiating something and seeing what the constant is. It might be that you've got products. Yet again, look at the fact when you've got product, is it the result of doing a chain rule differentiation? So because you've got x, which is something to do with the differential of x squared, you know that would have been the result of differentiating e to the x squared, so the answer to that integral is e to the x squared, and so on. You know that the differential of sine is cos, so that's something to do with the differential of sine x to the power 4, and so on. X squared is something to do with the differential of the bracket, so that's a constant multiple of the differential of x cubed plus 1 to the power 5. So you can just differentiate something and sort your constant out. If it's a product where there's no obvious link, like these, integration by parts. Normally, they tell you, use integration by parts to do these, so it's pretty good. We'll look at an integration by parts case specific to furthers in a little moment. Fractions. Be aware with fractions, if the bottom is to the power, the function to the power 1, it's probably a Ln answer. F dashed over F is what you're looking for. If it's not, if it's a root, or all squared or all cubed, then it's not a Ln answer at all. You've got to go back to one of the other things that are up above. So you're looking at differential at the bottom is 2x plus 3, so that's to do with Ln of x squared plus 3x plus 1. Differential of that is 2x, so although you haven't got the 2, you've got the x at least, so the answer will involve Ln of x squared plus 1. And the differential of cos is minus sine, so you know that will be minus Ln cos x or Ln sec x. What I'm going to look at, because I don't think I've done it so far, is I'll start off by looking at odd powers of sine and cos. So let's have a look at the 3 examples I've got today then. For example, if I look at the integral of sine to the power of 5x, it's exactly the same process if it's cos, if it's cubed to the power 7, you're not going to get much higher than that because it just gets ridiculous. So what I can do with any odd power, I can split it up as sine x times sine to the power 4x dx. So I need to the power 1 and then whatever's left there. Okay. With the even part now, I can use the fact that I've got cos squared x plus sine squared x equals 1 to make sine squared the subject, 1 minus cos squared. In this case, I know it's the integral of sine x times 1 minus cos squared x all squared dx. And what I'm going to end up with is multiply this out, 1 minus 2 cos squared x plus cos to the power 4x dx. And I'm basically now, I wouldn't necessarily write it out, I might write it out, just expand it term by term. I'm going to do it as 3 separate integrals. So I'm going to integrate sine x dx. I'm going to integrate minus 2 times the integral of sine x cos squared x dx. And I'm going to do the integral of sine x times cos to the power 4x dx. So differential of cos is minus sine, so the integral of sine is minus cos x. Now, if I was to differentiate cos cubed, I would end up with, well, let's have a look. If I just cos cubed x there, if I differentiated that, I get 3 cos squared x times minus sine x. So I've got that term there, but I would end up having to divide by minus 3, so I end up with plus 2/3 cos cubed x. And similarly for this one, how would I get sine x cos to the power 4? I would have differentiated cos to the power 5, so I end up with minus 1/5 cos to the power 5x dx in exactly the same way. If I was to differentiate cos to the power 5, I'd get minus 5 sine x times cos to the power 4 by the chain rule. And then, sorry, not dx, because I've integrated already, plus c. That's my answer. Okay, so my method for odd powers of sine cos is split it up as that to the power 1 times an even power. With the even power, rewrite this to get the other trig function in, and if it's to the power 4, I've got to square it. If it was to the power 6, I'd have to cube it, and so on, and then treat it as now, in this case, 3 different terms, and integrate each one individually, realising that the product is now, as we said before, the result of doing a chain rule differentiation. So that's the last of the ordinary integration, the single pure. I'm going to look at a couple of things now, which is to do with even powers of sine and cos. Now it might be, this is specifically to do with furthers. Now there's a couple of ways of how the question may go here. This might be a follow-on to a part A where you've done something else to rewrite cos to the power 6. I can't do even powers on their own. I can't do the method I've done before because it doesn't work. I end up with cos to the power 1 times cos to the power 5. Doesn't help me at all. So what I have to do here, I have to try and rewrite this as cos of multiples of x rather than as a power, and that involves Demar's theorem. So you wouldn't, I don't think, get this question on its own, but you would have to consider that we've got this idea here, 2 cos nx equals z to the n plus z to the minus n, which comes from our Demar's theorem of eliminating the I sine part of it. And what I can do with this one, if I want cos to the power 6, I want to consider 2 cos x to the power 6, which is whatever it is, 32 cos to the 6x, and that will equal z plus 1 over z to the power 6. When I expand it, z to the 6, 6 times z to the 5 times 1 over z becomes z to the 4, 6 times 5 over 2, 15, z to the 4 times 1 over z squared becomes z squared, 6 times 5 times 4, 3 times 2 is 20 on its own, and then we've got 15 z to the minus 2, 6 z to the minus 4, and then plus z to the minus 6. There's my 7 terms there. And I compare them together. I get z to the 6 plus z to the minus 6. And then I've got 6 z to the 4 plus z to the minus 4. And then 15 z squared plus z to the minus 2. And then plus 20. And I can rewrite that as now I've got 32 cos to the power 6 x, and that becomes 2 cos 6x plus 6 times 2, 12 cos 4x, and 15 times 2, 30 cos 2x, and plus 20. Divide everything by 32, and I end up with exactly what I'm after. Cos to the power 6x now is 2 over 32, 1 over 16 cos 6x, 12 over 32, divided by 4, 3 over 8 cos 4x, 30 over 32, 15 over 16 cos 2x, and 20 over 32, 5 over 8. So the integral of this becomes the integral of these terms now. So the integral of cos to the power 6x dx becomes the integral of this. And how do we integrate? Difference of sine is cos, so the integral of cos is sine, but I've just got to divide by 6. So I end up with 1 over 96 sine 6x, and plus 3 over 32 sine 4x, plus 15 over 32 sine 2x, and then plus 5x over 8, ordinary integration, plus c. And so in that case I've used my Demar's theorem to rewrite the power, cos to the power of something as multiples. I can now integrate multiples one by one, and that's how I do an even power sine and cos. This is really rare, and it's only for the furthers. Okay. Similarly, also only for the furthers is integrating my parts. I think it's going to be twice over. Let's have a look. I've got I equals the integral of e to the 4x cos x, oops, dx. So let's have a look then. In some ways it almost doesn't matter what's what. I can say u equals v dash equals, let's v dash equals cos x. Difference of sine is cos, so the integral of cos is sine. So u equals e to the 4x, and u dashed is 4 e to the 4x. So I becomes e to the 4x sine x there, minus 4 times the integral of e to the 4x sine x dx. So I've now got to consider I1 equals the integral of e to the 4x sine x dx. And yet again, u equals 4x, sorry, e to the 4x. U dash is 4 e to the 4x. V equals sine x now. Sorry, v dash. So v will equal minus cos x. Difference of the minus cos is sine. And so we now get I1 equals, I've got to be careful when I stick everything in, minus e to the 4x cos x, and then plus 4 times the integral of e to the 4x cos x dx. And our issue is this part here is exactly what we started off integrating. So when I stick this back into I get I equals e to the 4x sine x minus 4 times this, so it's plus 4e to the 4x cos x, and then minus 4 times that becomes minus 16. Oh, I. That thing there, I'm never going to be able to get rid of the e to the 4x and cos x. It never reduces to something that can integrate. But what happens when I do this twice, I get the same integral appearing again. So I can say that when I move it across, 17i equals e to the 4x, I can take that as a common factor, sine x plus 4 cos x. So I is e to the 4x over 17. Something I've missed. We'll see. Okay, so there's nowhere at all I can actually reduce this to anything that I can integrate. But when I do integration of my parts twice, even if I'd done the u and the v the other way around in various places, I should have still ended up with the same answer. So the idea is that the original integral appears again, and I can just, that's why using I equals makes this working quite nice. I can see it's there, and it all falls into place quite nicely. Okay, so that's how I would use integration by parts. Yet again, quite rare. It might not come up at all in any of the furthers you see, but it might do, so it's worth seeing just in case.